Given a basis for an ideal, we're going to find out how we could test if it's a Gröbner basis or not. So this is called Buchberger's criterion. First, a few notation. So if I take a sequence of polynomials, g1 through ga, then I'm going to denote the remainder of a polynomial upon division by this sequence as follows. Remember that our division algorithm associates to a polynomial where we're dividing by a sequence of other polynomials, a certain remainder. And so we denote this remainder by f bar and the sequence g. So if g was a Gröbner basis, then the order of the polynomials would not matter, but in general it does matter. Also, let's make it easier to refer to the leading monomial of a polynomial. So if the leading term of a monomial is a non-zero constant time x to the alpha, then we write the multidegree of f to be alpha. And given two monomials, we're going to define their least common multiple as follows. So if a and b are non-zero constants, then we define this least common multiple of ax alpha bx beta, and we call it to be the monomial x to gamma with coefficient 1, so we ignore a and beta, b, we ignore a and b, and gamma is a sequence of gamma i's, where gamma I is the maximum of the alpha i's and beta i's. So of course this monomial will be divisible by x alpha and x beta. And here comes the main ingredient for this talk. It's the S polynomial for a pair of polynomials. So here's how we construct this. We're going to multiply f and g by certain monomials in such a way that the leading terms of f and g will cancel, so that we have some combination of intermediate terms of f and g appearing as the leading term of s. So here's how you could do this. You could take the least common multiple of the leading terms of f and leading term of g. You then divide by the leading term of f and then multiply by f. So that gives me one of the polynomials, and then I subtract from it. Same thing for g. So I take the least common multiple again, same least common multiple, but I divide by the leading term of g and I multiply by g. So clearly the leading term of g will cancel this leading term here, and the same with f and the leading term of f. Therefore, the leading terms of these two polynomials will be the same. They will be a multiple of this least common multiple, and so they will cancel. So it's worth noting here that the least common multiple is of course divisible by the leading term of f, and same with the leading term of g. Therefore, this is simply a monomial times a constant, Therefore, the S polynomial is indeed just a polynomial. So a very important note is that the multidegree of S fg will be strictly less than the multidegree of the least common multiple. So here you can see that the leading term of this expression will have the same multidegree as the least common multiple, same here, but they will cancel, so I will have something of multidegree strictly less. Here I'm assuming that we fixed an ordering, a monomial ordering already. So let's do a simple example just to get a feel for this S polynomial. So I take these two polynomials and I order the monomials with respect to the graded lexicographic ordering, so that x cubed y squared is the leading term of f, and 3 times x to the 4y is the leading term of g. So the least common multiple is where we just need to read the highest power of x that's appearing here. This is x to the 4 times the highest power of y that's appearing here. That's y squared. That's it. So this is the least common multiple. And then the S polynomial of f and g is this least common multiple divided by the leading term of f times f minus the least common multiple divided by 3x 4y times g. So these will cancel, and then the rest I can compute. Okay, so since the leading terms are already going to cancel, I threw them away and then wrote the remainders here, and then you can open this up. Okay, so note that this least common multiple had multidegree 4, 2, the leading term of S, the S polynomial, is x cubed y cubed, and with respect to the graded lexicographic ordering, well, they have the same degree, but lexicographically this has fewer powers of x, and therefore the least common multiple really has higher multidegree, and that validates this remark here, so that the multidegree of the least common multiple is less than the multidegree of the S polynomial, so that's correct. And now we can state Buchberger criterion. It says the following. Okay, suppose we have a basis of an ideal I, given in some order, it doesn't matter. So this sequence of polynomials is a Gröbner basis if and only if the following holds. If when we compute the S polynomial for every pair of gi and gj, and we compute the remainder modulo g, then this remainder should be 0. So if this criterion is satisfied, we have a Gröbner basis and vice versa. So let's prove the easy direction first. Suppose G is a Gröbner basis, then the S polynomial belongs to the ideal, therefore the remainder will be 0, as we've shown before. So now let's go in the other direction. Suppose all reductions are 0, and we want to prove that G is a Gröbner basis. Okay, so the definition of a Gröbner basis is that the ideal of leading terms of I should be generated by the leading terms of the basis G1 through Ga. And this is what we want to show. Equivalently, I could show the following. I take a polynomial in I, and I would like to be able to represent the leading term of this polynomial via the leading terms of Gi's. Okay, then let's take our f and first just write it in terms of G, because G is the basis for the ideal. And now we observe the following. So if none of the leading terms of hi times gi is greater than the leading term of f, then we will be able to represent the leading term of f by this expression, by just taking these top degree leading terms. So let's write this down. So if you see, if the multidegrees are at most the multidegree of f, then the leading term of f must be representable by the leading terms of these hi, gi's for the i's where the multidegree is exactly equal to the multidegree of f. And I mean, I can write this down. So summing over the same i's, I can just write this as the leading term of hi times the leading term of gi. So clearly then the leading term of f will belong to this ideal of leading terms generated by the gi's. And we would be done if we could show that for every f we can find such hi, gi, so that this condition here holds. Now this condition cannot be for free, and I'll show you an example. And now we have to work hard actually to prove that this condition holds when our assumption about the S polynomials, which is this assumption that all the S polynomials can be reduced to 0, when this holds, this assumption holds. Since this will require some work, let's pause the proof here and then think a little bit about what's happening. So let's say this is now a half completed proof. In particular, if you're willing to believe that we can always find such hi, gi, then you're basically convinced about this Buchberger's criterion, and this gives you a clearly algorithmic way to check whether a basis is a Gröbner basis, because the computation of the S polynomials are purely algorithmic, very simple expression. Division, multivariate division, and computing the remainder is algorithmic. Therefore, this is a clear binary test. And if you're not worried about this condition, let's make an example first. So I'm taking the following polynomials, xy minus 1 and x squared minus 1. We've seen them before, so these certainly are not a Gröbner basis. In fact, we've seen that the following equality holds. Alright, now I'm going to use the G-lex monomial ordering again, so that these are the leading terms here. this x is the leading term here. And let's open this up. So the leading term, or let's say the multi-degree here, is going to be y times g2. That's 2, 1. Of course, the same thing here. This is also multi-degree is 2, 1. So that's x times xy. Here, however, the multi-degree was 1, 0. The leading term is x. And clearly, 1, 0 is less than 2, 1 with respect to GLX. So there's no way you're going to write x minus y as a combination of g1 and g2 in such a way that the multi-degrees are less than or equal to 1, 0. Because already the multi-degrees of g1 and g2 are going to beat the multi-degree of x minus y. So that this condition that we're assuming here about the existence of such HIs is a non-trivial assumption, and it must come from the null hypothesis about the reducibility of S-polynomials. Now, in order to continue the proof, we need a couple of lemmas. Okay, now let's suppose that we found HI where the multi-degrees, some of the multi-degrees, are strictly larger than the multi-degree of f. If we just look at the i's for which the multi-degree is strictly greater than the multi-degree of f and consider their sum, the leading terms must cancel because on the left-hand side there is nothing of sufficiently high multi-degree. And we will show that such a condition can be explained in terms of S-polynomials. Let's write this down. Let's take a bunch of polynomials, each having the same multi-degree delta, and we're going to show that if the multi-degree of the sum is less than delta, then we can represent this sum in terms of S-polynomials, each of which, by the way, has multi-degree less than delta. So I'm saying that the sum is in fact a k-linear combination of the S-polynomials. So k's here are base field as always. And the proof is actually very simple. So we can write each of the pi's as a constant times x to the delta plus lower order terms. And then the constants must satisfy the following. The sum of the constants should be 0 since the leading term x delta cancels out in the end. The S-polynomial of pi and pj will also be super simple, so let's compute this. The leading term of pi is just ci times x delta, so the least common multiple of these terms is just going to be x delta. So I have x delta here divided by ci x delta times pi minus x delta cj x delta pj. So okay, these things cancel. I have ci inverse pi minus cj inverse pj. And now the lemma probably already looks like it's going to be trivial because, I mean, my S-polynomials are just some linear combinations of pi's and pj's. It's probably already clear to you that I can do this. But let's finish this off explicitly. So I'm going to sum over all these S-polynomials, but I'm going to sum from I goes from 1 to s minus 1, and then let's compute the s pi ps. So that's the last polynomial, and I'm multiplying by ci. So that's going to give us, so just expanding out the s polynomial, I get this already, and then let's write it like so. And now collecting terms, I have sum of pi's up to s minus 1 and then the coefficient of ps. But the sum of all coefficients from I from 1 to s was 0. Therefore, minus s is in fact equal to this partial sum. So this coefficient is 1. And that concludes the proof. So I've given one representation. So my Cij's ended up being Ci's or zeros. Okay, then let's continue the proof of the theorem with this slight interruption. So what we want to do now is to assume the worst so that we have f equals sum over HIGI, but the maximum of the multi-degrees of HIGI is, let's say, delta, which is greater than the multi-degree of f. So in this case, we cannot conclude the theorem saying that the leading term of f is representable by the leading terms of GIs. And what we want to do is to say that in this case, I can find different coefficients for gi's so that the multi-degree, the maximum of the multi-degrees, will be strictly less than delta. And if that means I can keep repeating this procedure until I hit the multi-degree of f and conclude the theorem. So our goal is to find better hi's. So let's write this as follows. We have leading term of hi times gi, but over all I, only when the multi-degree of hi, gi is delta. So this is, I'm collecting all the highest terms into one summand. So same I as this one, but now I want to say hi minus the leading term of hi times gi. Okay, so that when you collect them, I collect the hi's with high multi-degree, and then let's say the other i's. So this is just hi gi. Observe that here the multi-degree is going to be strictly less than delta. Here this multi-degree is strictly less than delta. The only offending term is this first summand. So if I can find some coefficients of gi that is able to represent this sum, but where each coefficient has less multi-degree, so that these products have multi-degree strictly less than delta, then I will solve my problem. Okay, so here in this sum, I can use all of my gi's, and then I'll be done. Now let's rewrite this summand, but we can attack this problem in general, so I don't have to keep track of the hi's. So here's the problem we're trying to solve. So let's take pi's that are just monomial times the coefficients times gi, so that the multi-degree of pi is delta, and with the sum of pi's having multi-degree less than delta. Right, so that's exactly the condition that we have over here. We then know that this summand can be written in terms of the S-polynomials. That was our lemma. So here I've written this green box as this sum in terms of the S-polynomials. Right, so that was using our lemma. But now I can simplify my problem further. All I need to do is to show that these S-polynomials can be written in terms of the gi's with each summoned hi tilde gi having multi-degree less than delta. But let's analyze these S-polynomials. So I'm only going to consider the cases where the coefficients are non-zero, of course. That's all that matters. So ci, cj are non-zero. When we compute this S-polynomial, it's going to be related to the S-polynomial of gi and gj. So this is a simple exercise. Let's call it exercise. The ci's that are appearing at the bottom when I read the leading term of this expression will appear at the bottom, and it will appear again when I multiply by that term here. So the ci's will cancel. Also x to the power delta minus delta i's that should appear at the bottom and at the top will also cancel. It's clear that you get this expression. But this is equal to, so x delta minus some, let's call it gamma ij, times the S-polynomial of gi gj, where gamma ij is the multi-degree of the S-polynomial of gi and gj. Sorry, this is not the multi-degree of gi gj, it's just the multi-degree of the least common multiples. So that's what we would have put in here. We would have put x to the power x gamma ij here for the least common multiple. Delta is something necessarily larger, and I can obtain the S-polynomial then by taking out this x to the delta minus gamma ij. Okay, now finally we're going to use the hypothesis that the S-polynomial could be reduced to zero modulo our g basis. Okay, then since the remainder upon division is zero, then our division algorithm will just produce us these coefficients qij, k. So for this ij, I have a sequence of polynomials indexed by k. And remember that our division algorithm also had satisfied the following property where these quotients had small degree. And now multiply this S-polynomial by this monomial term over here. And let's look at the new terms that appear here. This thing has multidegree less than or equal to the multidegree of the S polynomial plus the term that we're translating with. But remember, the multidegree of the S polynomial satisfies the following. It's strictly less than the multidegree of the least common multiple of the leading terms of Gi and Gj, which we define to be gamma ij. So since this multidegree is strictly less than gamma ij, I use this expression here to say that this multidegree is strictly less than delta. Now this allows me to conclude the proof, because let's go back up. Our goal was to write this expression as a sum of gi's so that each term has multidegree strictly less than delta. And I said, well, let's call each of these terms pi's, write it in terms of the S polynomials as a k-linear combination using our previous lemma. And then I computed the S polynomials and related it to the S polynomial of gi, gj's up to a multiple of x. Now our goal is just to show that each of these summands, so each of these S polynomials, can be written in terms of g's, where each term has multidegree less than delta. And then that's exactly what we did. We used the fact that each of the S polynomials of gi's and gj's reduced to 0 to cook up this expression where the S polynomials of pi, pj, that's what this is, can be written in terms of gi's, gk's, where each term has multidegree strictly less than delta. So I can play this game again and again until the multidegree of the terms that I use to represent f here, all of them eventually reach at most the multidegree of f. And then in this case, we have already concluded a theorem saying that the G has to be a Gröbner basis. Well, okay, so this establishes Buchberger's criterion, which means that if someone hands us a basis, we can check whether or not it's a Gröbner basis. In general, this is not good enough because people are not just going to hand us a Gröbner basis, which means that the next thing we do has to be about generating a Gröbner basis for an ideal. But the key item is Buchberger's criterion, so what we just proved. And we will talk about finding a Gröbner basis in the next lecture. See you then.